So now we're going to look at the kinds of waves that are generated by earthquakes. So the first kinds of waves are kind of like when you have a slinky and you push the slinky in and out. So when you do that, you're going to generate a wave, and these are called primary waves or body waves. So you can see here, you shake your hand back and forth, and as you do, you're sending out a wave that's traveling along the length of the slinky. So these kinds of waves are called primary waves, and they travel inside the earth. So body waves travel inside the earth. So these primary waves, and another word for them are P waves, or even you can even say, because of P, you can call these push-pull waves, because it pushes and pulls on the earth as it moves. And these P waves can travel through solids. So let me just say travel through also. So they can travel through solids, and also liquids and gases. And as far as the shaking, they have the smallest amount of up and down shaking. What that means is that if you're standing on the ground here, the wave is going to pass you and you're not going to notice that much because you're not moving, it's not forcing you to move up and down. It's only moving side to side. So next are going to be what are called secondary waves or shaking waves. These are waves that actually, as the wave travels in this direction, it shakes the wave up and down, or it shakes the ground up and down. But these waves also travel inside the earth. They're body waves. So the next kind of wave we're going to look at are called secondary waves. Or S waves for short, or even shake waves. And these waves only travel through solids. So I have simulations at the end of the PowerPoint. So I highly recommend that you watch the simulations to see the difference between these kinds of waves. So there's another kind of wave. You're not gonna be tested on it, but it's still good to know. It's called the surface wave. So these are the ones that you tend to experience when you feel an earthquake. So what ends up happening is that inside the earth you have the S and the P waves that pass by, but then there's also on the waves that travel on the surface of the earth. So these are called surface waves. And these surface waves actually make the surface of the earth vibrate up and down and side to side. And these are the waves that topple buildings and cause devastations. So here, let's compare all three of them. Let's see how we can compare them. So if an earthquake were to happen, let's say over here, and you have a sensor here, which wave would arrive first? So if you notice, there's a couple of ways that you can look at this here. So let's actually look at the first one. So this is after the earthquake, so let's look at this station over here. So this is in terms of time. So then this is early, and then over here this is later. So when the earthquake happens, all of them, the body waves travel through the earth, and the first wave that's going to arrive is going to be the primary or push-pull wave. And then the next wave that's going to arrive from this safe station here is going to be the shake waves. And both of these waves travel inside the earth. And the last wave to arrive is the one that causes the devastation, and that's going to be the surface wave. So the surface wave travels along the surface of the earth, and as it does, it sends those surface ripples that cause the devastations, and these arrive last. So in terms of speed, the P waves, the push-pull waves, are the fastest. So you can see it again here. The first wave that arrives are the P waves, the push-pull waves. The second waves to arrive are the shake waves. And the last wave to arrive at that location are the surface waves. But they're the ones that topple the buildings. So here, this shows you the distributions of earthquakes across the globe, and you can see an interesting pattern. So here you find that you have the most amount of earthquakes. So you can see here the global earthquake belt. So you can see the region where you have the most amount of earthquakes here corresponds to this region over here. And if you look at the types of plate boundaries that you have over here, these are the blue regions. So these are the conversion boundaries where you have the megathrust faults. So again, this is where you have the most devastating earthquakes. So we're not going to talk much about the earthquake scales, but some of you might have heard of Richter scales, but there are some other scales that are used also, but we're not going to spend a lot of time on this. But now, though, we're going to learn about tsunamis. So how do tsunamis work? Tsunamis are related to or byproduct of these megathrust fault earthquakes. So again, you can actually see it in the visualization of how the megathrust fault works. So what's happening is that you have the oceanic crust here making contact with the continental crust, and as it does, friction is dragging the crust down. So you can see this was the original way that the continent looked, but friction drags the crust farther down until friction can't hold, until the friction can't hold the two plates together anymore, and then the whole thing just snaps back and you get the earthquake that occurs. So now that was the megathrust fault, but let's see the consequences of that. Now when the crust snaps back, so when it snaps back into position, it pushes a huge amount of water upwards, and as that water moves upwards, it sends these humongous ripples outwards. And as these ripples approach shore, you get a tsunami. So let's see how the tsunami works. So let's just define what we can for now. So first of all, tsunamis are created when you have large ocean waves. Well, tsunamis are large ocean waves that are created when megathrust faults lift a huge slab of the ocean floor. So it lifts a big slab of the sea floor. It should be slab. I put slab. So slab of the sea floor. So what do you notice? Well, let's actually, before it arrives on land, let's see what you notice when you're in the middle of the ocean. So in the middle of the ocean, interestingly enough, tsunamis are barely visible for two reasons. So here, the top of one wave of a tsunami, the distance from the top of one wave to another, can be as much as, let's see if I have it here, they can be as much as 400 miles across. So for you to see one wave, I mean, it's almost past what you can see across the horizon. So the distance from the top of one wave to the top of another can be as much as 400 miles across. And the other thing is that, well, there's two more things. The height of the wave is barely above, is not that high at all. It can be less than 3 feet high. So the height of one wave above the what the normal height of the ocean can be 3 feet high, again, making it hard to see. And the last part is that this wave can travel as fast as an airplane. So I'll just say very fast. So because of that, tsunamis in the middle of the ocean are hard to detect. So in the middle of the ocean, they can travel 500 miles per hour or as fast as an airplane. So just 500 miles mph. And all those things make tsunamis hard to detect when they're in open ocean. The top of one wave to the top of another is just too far to see. The height of the wave is too small to see, and it's moving extremely fast. So middle of the ocean, tsunamis are hard to detect. And again, I recommend that you watch the computer simulations that I have in the back that show you the creation of a tsunami. But what happens when a tsunami approaches land? So let's see if I can draw this picture here. So let's say that this is the continent going down into the deep ocean, and then you have the tsunami that's arriving. So this is going to be the tsunami here. So what do you see when a tsunami is arriving? I'm kind of exaggerating here. And let's say that, maybe I'll try to modify this some. Let's say that this is the shore of the beach here. And then it goes down. And then you're standing here. So what do you see when the tsunami arrives? So when a tsunami arrives, this is what you see. So first of all, I guess I should probably draw this a little bit better here. So there's like a dip because of the long wavelength, and let's say it looks something like this. So what do you notice? As the tsunami arrives, what you notice first is not a big wall of water. What you notice first is the dip of the wave arriving. And following that, and here this is gonna, and following that, that's when you see the wall of water approaching. So tsunamis are deceiving because the first thing you're going to notice is because there's a dip in front of the wall of water, first you notice that the water that you're standing in recedes, it moves away, and after that, then you get a big wall that comes in. So I believe that's what you're going to see on the next slide. So this is going to be one clear signal of an approaching tsunami, is that you can be at the beach, and if the water recedes farther than normal, that's an indication that a tsunami is approaching. Because again, what's happening is that this is you on the beach, and as the tsunami is approaching, the first thing that happens is that there's a big wall, but before it, there's a big dip. Because again, it's kind of hard to draw this to scale, but these are big waves here. And so what you're seeing first is the dip of the wave before it arrives. And as that dip arrives, then if you can see here, you notice a dip arriving at the shore, and then comes the wall, which is what creates all the damage. So one clear signal of an approaching tsunami is a rapid withdrawal of the water. So an approaching tsunami a signal of that is the rapid withdrawal of the shoreline water, and it goes back farther than normal.